Hi, and welcome to NASA Launchpad. I'm your host, Isaac. Micropulse, multi-beam, photon counting. Sounds complicated, doesn't it? But if you've ever played with the green laser pointer, you may already have a jump on the advanced technology that NASA is using for its newest ice monitoring satellite, ICESat-2. The original ICESat mission operated from 2003 to 2009 and helped NASA scientists study sea ice and ice sheets, detecting some dramatic changes in Earth's cryosphere. But why study ice anyway? Ice can actually have an enormous impact on weather and on global climate. Sea ice keeps the polar regions cool and helps moderate global climate. Sea ice has a bright surface, so much of the sunlight that strikes it, about 80% of the light in fact, is reflected back into space. As a result, areas covered by ice don't absorb much solar energy, so the temperatures remain relatively low. As sea ice melts in the summer, darker ocean surfaces absorb the sunlight. The oceans heat up, which in turn heats up the surrounding atmosphere, causing Arctic temperatures to increase even more. Even a small increase in temperature can lead to greater warming over time, making Earth's polar regions the most sensitive areas to climate change. So, it's really important that we keep a close eye on what's going on in these icy regions near the North and South Poles, and that's just what ICESat helped scientists do.
ICESat was NASA's first laser altimeter in space, and ICESat stands for the Ice, Cloud, and Land Elevation Satellite. ICESat was a benchmark mission for NASA's Earth Observing System fleet of satellites, and it provided a reference point for ice sheet mass balance, sea ice thickness, vegetation biomass, and cloud structure. Some of the major findings of the ICESat mission were that the Greenland ice sheet is losing a lot of ice every year. We take all that ice and put it into the ocean. That's enough to raise the ocean sea level all over the world by a few millimeters, and that happens every year.
After the ICESat mission came to an end, engineers went to work on a new design to get better coverage of the Earth. Now, ICESat-2 is all about measuring elevation. But exactly how does it do that, and how does this new design overcome limitations of the first satellite?
There were three components to figuring out the elevation measurement. We need to know where the satellite is very accurately. We need to know the direction that the laser is pointing, and we need to know how far the laser pulse traveled when it went from the satellite to the surface of the Earth. With those three pieces, we can actually calculate the height, the elevation of a particular spot on the surface of the Earth.
ICESat would send out small pulses of light and time very precisely how long that light took to go from the satellite, bounce off the Earth's surface, and back to the satellite again. By measuring that travel time, we could learn about the height of the Earth beneath the satellite. And over time, we were able to build up maps of the shape of the ice sheets, the thickness of sea ice, and the height of forests all over the world. Now, the detectors on ICESat-2 are so sensitive that they can detect individual photons of light. That's the smallest unit of light that we have. So ICESat-2 will send out millions of photons, and of those millions it sends out in each pulse, we'll record 5, 6, 10 signal photons. And those 5 or 10 photons are what we use to make our elevation measurement. We know precisely when they left, and we know precisely when they came back again.
ICESat carried 3 lasers that operated one at a time. Just like ICESat, ICESat-2 has multiple lasers to ensure long-term operation. The lasers shoot a single laser pulse. The pulse then splits into 6 separate beams. What's the advantage of this high beam technology? Let's turn to the experts to find out.
So when we talk about ICESat-1, ICESat-2 is the follow-on mission to ICESat-1. And whenever we do things at NASA, we like to improve upon the technology that we've developed in previous missions.
With ICESat-2, we're using a much smaller beam that illuminates an area about 10-meter circle. So it's a much finer precision measurement. In addition, ICESat-2 fires its laser much more frequently. So instead of one measurement every 150 meters as the satellite flies, ICESat-2 will give us one measurement every 70 centimeters as ICESat-2 flies. So it's much smaller footprint and much more dense spatial sampling.
The statistics collected about the cryosphere by ICESat-2 will be organized into data profiles and studied by scientists all over the globe. But what is it they hope to understand?
So ICESat-2 is measuring height. It's an altimeter, so you're going to get very high resolution, very specific levels in terms of data. And so we have researchers, we have scientists that are looking at the level of water in a reservoir. That is something that you wouldn't necessarily think of right off the cuff when you see the name ICESat-2, because you automatically think ice. But it has different applications beyond that of the cryosphere. So you have reservoir heights, you'll have vegetation canopy heights, then you have, again, your sea ice thickness, and then your land ice. I think you can really be creative in terms of how you use the data, which is why we go outside of the scientific community and look at different ways operational users could really value altimeter data, because it's not just what's in our head, it's really combining what's in other people's heads. And I think once you get all these creative minds working, you can find different ways of applying the data.
So that's it. With ICESat-2, NASA is staying on top of technology and advanced cryospheric research. And with each pulse of light, ICESat-2 is putting Earth in perspective. Thanks for watching. I'm Isaac, and we'll catch you next time on NASA Launchpad.